Thanks, everyone. Thank you. Building Ruby extensions in Rust, I'm going to talk about the journey of building it. So I will kind of cherry pick the most challenging things that I encountered when I was building this. And yeah, I hope by the end of this talk, you can build one yourselves. But before that, who am I? My name is Guilherme Carreiro. I'm actually from Brazil. I was born in a place called New Europe in Brazil, and now I live in the old Europe. And everyone knows about Madrid, so I don't need to talk about this. But about New Europe, one important thing that we have is that we have the largest shopping mall in Latin America. So this is our special thing. And one special thing about this shopping mall is that my mother bought my first programming book at this mall. So when I was a teenager, I was learning about logic, and I started writing programs. In the beginning, I started with Macromedia Flash and ActionScript and Delphi and building very silly programs. And then I learned that I really loved to program, and that was my beginning. Now, 20 years later, I'm working on Shopify. I work with developer tooling, more focus into the liquid developer tooling. So when folks are building Shopify themes and they have code completion, is because of the work that my team is doing to the language server, the grammar, the coding highlighting, all the tooling around liquid. This is the thing that we're responsible for. And there's a lot of stuff that involves liquid, right? Because you need to do it yourself when you're developing, and we also need to render. So this is a bit of my work as well. When folks, they open a shop and that page renders, all the parsing work, and that happens into that site, I'm working into that side as well. So this is a little bit where is my work. Of course, render storefronts is a performance critical thing, and doing developer tooling is also a performance critical thing. Like when you're writing our code and the code completion doesn't load, it's a bit frustrating. We have as a metric that we have 100 milliseconds to show some clue for developers. So they are writing an object, and they type a dot. We have 100 milliseconds to realize the property is available there. So we need to do some type inference. A lot of stuff happens into this process. So developer tooling is also a performance critical thing. And that's a bit what I do. And by working into this project, I had the opportunity of building a native extension, not because I wanted in the beginning, but because I needed. And when we think about native extensions in Ruby, the first thing that we think is, okay, I'm going to need to do this because of performance. It's going to be faster, so Ruby is slow, I cannot use Ruby. And I believe that's really debatable. Here we have an example of some computational thing happening in pure Ruby. And let's say that this computational piece here is critical for your business, it's critical for your company. You really need to make this fast, and then you say, I'm going to extract this to a native extension in Rust, it's going to be faster. And then you learn how that thing works, get excited, and you say, you know what, I'm going to extract everything. And then you have these 3 versions of the same code here. But look at this, you can think, which one is faster? And for sure, the 3rd version here is the fastest one. However, the interesting thing is that the 2nd fastest one is the pure Ruby version, and the 2nd one is the slowest one. So in the 2nd one, we introduced all problems and complexities that bringing a native extension brings to your project. We're bringing all of that, you're not having any benefits from this. So this is the first thing that I would advise. If you really think that a native extension can solve a performance bottleneck in your application, first of all, there's other alternatives. And second, prototype, because during this prototype, you can realize if it can really solve it. Because, of course, native extensions, they introduce that overhead of having your Ruby program here and facing the FFI boundary to reach the Rust land. So we always have everything has a price here. So that's the importance of the prototype. And that's the thing that we're going to do today. We're going to build a native extension together. We're going to prototype it. And one interesting thing about Ruby is that we use a lot of YAML files, right? We use these for database configuration. use this for our linters. We use YAML files all the time. And because of this, we can guess that Ruby has a very strong and good YAML parser to be able to read that file, get the properties, and configure your project. So I have this hypothesis that Ruby has a very good YAML parser. And I also have the hypothesis that Rust has the best TOML parser, because all configuration files in Rust, they are, by convention, they are TOML files. So my guess is that Rust has the best TOML parser that we can find. So with this in mind, what if today we build a native extension that's a Ruby gen that you can install in your project to parse your TOML files, and let's make that gen really, really fast. And the first thing that I needed to do to validate my idea is double check if other folks are not doing that already, right? So the thing that I did was, let me double check the most used TOML parsers that we have, and double check if they are already using this architectural approach of parsing the TOML file using a native extension. The good thing is that they are all open source, so I could double check the code base there and confirm they are not using that approach. So that means that I can build a TOML parser gen that's really fast. So the first thing that we're gonna do is this. We're gonna create a gen just like we are used to do it, but we're gonna use this ext flag and pass Rust as a parameter. This is quite similar to the same process that we follow to create a standard gen, like we're doing here. And in a moment, we're gonna notice that the difference are only these 3 files there. What are these 3 last files? The cargo.toml, the xtconf, and the lib file. And the lib file. And what's special about these 3 files that are not included on standard Ruby gens? Cargo.toml is the gen file for Rust projects. So it's pretty much this. You don't need to think a lot about this one. The xtconf is a file that all native extensions being written in C or being written in Rust need to have. This xtconf file is a file that creates a very specific recipe when the users of your gen install it into their machines. And during the installation, that file gets executed. And for example, if they are installing your gen on Windows, this file is gonna have all configurations and complexities and dependencies that we need to install to be able to build this native extension from source on Windows. The same for Linux, the same for Mac. This file is a recipe that describes how users of your gen can build it from scratch. And the last one is only the source code of our Rust gen. So if we open this boilerplate here, as you may notice, we have this very simple init function here. The very simple thing that this thing is doing, this boilerplate code is doing, is I have this TOML module here, and I'm gonna define a singleton method into this TOML module that's called hello. And when that gets called, the function that's executed is this hello function here. And in this function, returns a string that interpolates this subject. So this is quite simple. And that's pretty much this that this Skull would have. And if we open the entry point of our gen, we don't have anything there. There's no code. There's one interesting thing, though, in the fact that this doesn't have any code. It lives in the fact that we have this require into the line. In the line 5 here, we have this require fastTOML, which is the name of our gen, fastTOML / fastTOML. If we investigate our code base, this file doesn't exist. There's no code in the entry point of my gen, so how this works? That's a question that we can ask ourselves. So let's try to execute this. And if we try to execute, this is the error we get. That file doesn't exist. So it seems like this gen doesn't work. So that's the second thing that we need to do after we create our gen. We need to bundle install to download the dependencies, as we always do. And we need to compile our native extension. So that Rust code is going to be converted to something called shared object that we're going to understand a little bit later. And then the Ruby code will be able to call that code that is written in Rust. And for Ruby, it doesn't matter if you're writing this code in Rust or in C. It really doesn't matter. It's the same infrastructure. And as you may notice here, we can now call our method, and it just works. So this was the important step. We needed to compile our gen, and then we got this fastamo.bundle file. This file here, it's going to have different extensions depending on the platform you're using. If you're using Linux, it's going to build a fastamo.sco file. If you use Windows, it's going to be another one. So depending on the platform, the bundle that's built, it's different. And they call this shared object. So this is how the things works. They work end-to-end. You can create your gen, you compile it, and then you can execute. But everything looks very magical, and we don't like this, right? We like to understand how things are really working. The reason that's very easy to do this is that there's a lot of libraries. There's not a lot of libraries, but there's some libraries that are helping us. So let's ignore those libraries. Let's pause this prototype for a minute, and let's understand how native extensions they work. And this is the most important slide of the talk. Here we have a Ruby program invoking a native extension, and we have no libraries involved. And here there's no magic. It's pure Ruby running. But it's difficult to digest, so let's digest together. The first thing we want to do is to execute this code. We want to call Ruby, and we want to execute this put hello from Rust. If we execute this, we're going to get an error. This hello from Rust variable or method, it doesn't exist. So let's do the second thing. Let's require something that's this simplest Rust extension. And the simplest Rust extension is the thing that's going to have this method that doesn't exist. And how we're going to put this method inside of this thing that we're requiring, right? Then we have the second line here. What we're doing here, we're taking a Rust source and compiling it to a bundle that Ruby can understand. And this bundle is compiled in such a way that it's already compiled, but can be dynamic linked into a Ruby program. So this is the thing that we're doing here. We're taking this simplest Rust extension.rs file, and we are compiling it into the simplest Rust extension.bundle. And we're compiling this using some flags, so the bundle can be dynamically linked into a Ruby program. So this is the thing that we're doing. And what we have inside of this simplest extension.rs, we have one important thing here. We have a function that starts with this init word here. This is a convention when it comes for native extensions. When we're building native extensions, again, being in C or being in Rust, we need to follow this naming convention, init, the name of your module. And when you follow this convention, the Ruby VM, when it needs to require that file, it knows that this function is going to be executed. So when this file gets required into the Ruby runtime, this RB-defined global function is executed. So we define a global function that's called hello from Rust, and this global function here, in the end, is going to call this hello from Rust function. It's a Rust function that returns a Ruby string. So it's pretty much this, and in the end, we just need to say to Rust, please trust me that RB-defined global function and RB-strnew, these two functions here, they're going to be available in runtime. So while you're compiling it, you can just trust that in runtime, these two functions, they're going to be available. And they are available here when we call our Ruby program. So this is how things work end-to-end when you need to have a native extension. Again, being C or being Rust, it's the same. Back to our prototype, why everything is so easy there? Because we have these two libraries that support us when we write in native extensions in Ruby. using Rust. We have Magnus, which are the high-level bindings. What that means, right? It means that when you are you have your Ruby program, right? At some point, your Ruby program invokes a method that lives inside of the native extension. And inside of this native extension, we're going to perform a very heavy work there, something that's computationally difficult. And then we're going to do that job. And in the end, we need to return the result of that very difficult thing to do, maybe a parser, for example. And then, in the end, we return the value to the Ruby land. To return these to the Ruby land, we cannot return the data types that we have in Rust or the data types that we have in C. We need to instantiate them into Ruby, so we return a Ruby string. And this is the thing that Magnus helps us. Magnus, it knows the right way of creating Ruby strings. So when you need to create a Ruby string, you just call Magnus, and it creates for you. So you can be pretty sure that you're not going to have memory leaks and stuff like this. And what RBCs does? RBCs has the C bindings and all low-level infrastructure that we need to work. So Magnus uses RBCs. We, as native extension developers, should never really need to do it, but maybe if you need to do something unsafe, then you can call RBCs directly. But you shouldn't need to do this. Everything that you need to do to build a native extension should live into the Magnus side. RBCs is something that we know that exists, but it's unsafe. It's unsafe to use. We really need to know what you're doing there. So we have these two libraries: the low level and the low level and the high level one. So cool. Back to our TOML prototype. We want to build a TOML parser. So we want to build something like this: a function that receives a string, parses it with something that's difficult, and then returns a Ruby value. So let's do this. So here we have our example from the beginning, our hello world example, and then we can just tune it a little bit, and let's pay attention to this parse method here. The thing that's doing is taking that string as a parameter, and it's using the Rust library to parse it, and then we take that value and we just convert that value to a Ruby value using this toRubyValue function here. So it's simple as this, the code that this native extension has. It uses the existing library to parse, takes the parse the result, and converts to a Ruby value, to a data type that Ruby can understand. And now you're probably thinking, how will you convert this value that exists only into the Rust land to Ruby? You can do that by doing something like this. You can take that value and visit it, and depending on the type, you're going to do a different thing. So you visit that value. If it's a string, you convert to a Ruby string. It's a hash, or a table, you convert to a Ruby hash. And then you visit this file, and in the end, you're going to have a data structure completely visited with all data types that Ruby understands. So it's pretty much this. It's a very short prototype. Now you can benchmark and double check it. To benchmark the thing that I did was I created this TOML input here into my Ruby file, and I benchmarked to double check, comparing my parse time with all other parse solutions that we have for parsing TOML files. And the results are very good in the end. Like the fast TOML, the gen that we just built with 2 functions, is the fastest one, and the second fastest one is almost 3 times slower, and the next one is like 16 times slower. So it's a visible performance enhancement that we have here. I also did other benchmarks to compare the parser from different perspectives, but the thing is, it's a fair improvement. So I want to go ahead. I want to take this gen and put in production, because let's say maybe you have a business need where you really need to parse TOML files really, really fast when you are doing something or rendering something or doing some developer tooling. But the thing that we need to do to put this in production is to fix some stuff that you left behind. The first thing is error handling. Here in the prototype code, we have this unwrap thing. What this means in Rust is that we're taking this string, we're parsing this string, and we're saying, trust me, the parser is going to work, just give me the successful result. However, if, for example, if your input, if your string has a syntax error in your YAML file, then this line here is going to fail, as we're going to notice here. So we can call the console, we can call our gen here, and if we pass an invalid YAML file, this is the thing that happens. We get this fatal exception. Fatal exceptions, they are no good in our Ruby programs. They can stop our execution, so this is not a nice thing. So the important thing that we need to do when we are building a RubyGen with a native extension is that we should have no panics into our program. And the way to do this, we can just remove this unwrap call here. So instead of doing this and doing what we were doing before, we're going to ask to the parser here, like, YAML, please take that value from this string, and if the result is this OK result, we convert this to a Ruby type. If it's not a OK result, then please create an error for me. And here we have another interesting convention that Magnus helps us, because this method now no longer only returns a Magnus value, it returns a result. And this result can be a Magnus value or a Magnus error. Into the Ruby land, when this method gets executed and the return type is a Magnus error, we're going to raise that exception. So we don't have this data type into our Ruby program. Or we get the result, or the error that we are creating here gets raised. And here we have, just for future reference, this is how we create errors when we are we are into the Rust land. We pretty much take the module of YAML and we define an error there. So it's just some prolix code to create an error class. But cool. And then we have it. And if we execute again, we can notice that now we get that fast YAML error that we want. So cool. Our gen is fast. Our gen handles errors well. The next step to double check before putting a native extension in production is double checking for memory leaks, because that's no good in production as well. And maybe someone would say, like, oh, Rust programs, they are, everyone says, like, Rust is safe, so you don't need to be concerned about memory leaks when you're writing this kind of program. But that's not true. Here we have a Rust program that has a memory leak. And the reason is that we're using this unsafe statement here. And then we can probably think, oh, okay, I can just not use unsafe statements into my program, and then I will have 0 memory leaks into my gen. However, are your dependencies safe as well? It can be exhausting to check the code base of all dependencies that we have, and the dependencies of the dependencies, just to be sure that nobody's using unsafe. And the truth is, sometimes they will be using unsafe in a safe way, which is interesting. So the only way to really be sure that we can put this in production is measuring. And then we can use some tooling to do this. You can use vulngrind. And vulngrind helps us to double check if we have some memory leak into a program. So, for example, we can execute this program here that we have. And in this program, we can clearly notice into the output that we have 4 bytes there into the definitely lost section. So we do have a memory leak into this program. And this is no good. Generally, we're not so concerned about memory leaks when we are programming Ruby, because in Ruby we have our garbage collector to collect all the reference for us and be sure that we don't have leaks. But the same is not true when we're writing a native extension in C or in Rust. So it's really important to measure this kind of thing and be aware that we need to manage the memory ourselves. If we do this into our gen the way that's right now, This is the output that you're going to get from VonGrind. It's quite exhaustive. We have a lot of stuff happening here, but this is not our program. This is the Ruby VM running into the program. And when you measure to double check the memory, we get a lot of noise. So it's really difficult to separate what's the Ruby VM and what's my program. Like, it's difficult to really understand. You still can do it. You can do some benchmarks, double check how numbers are fluctuating, but the approach that I recommend is using Ruby main check. With Ruby main check, it uses VonGrind under the hood, but it removes a lot of noise. So you can you can execute your program, use Ruby main check, and it's gonna give you a clearly signal if you have or if it do not have an issue there. Also, the Ruby main check has a GitHub action. So, for example, you can add this into your repository, and every time that someone opens a PR into your gen, that thing is going to run, and it's going to double check if you have a memory leak or not. So it's really useful into that side. So cool. We created our gen. We validate into the prototype. That's the fastest possible implementation, so we want to make it production ready. We did the error handling, we checked the memory, and refined from all those perspectives. So now let's publish so folks can use it. However, if you publish it, folks, they're going to see this message for a long time, because when they install your gen, it's going to invoke that confxt.rb file that has the recipe to compile from source. And that takes a long time. And then I was thinking, how the good gens, they solve this kind of thing? And then I double-checked was time. And the thing that they do is they pre-compile everything. So if you are working, for example, on Mac, you install wasm time, you don't need to compile all the things from sources, download the dependencies. You just download that bundle, and it's ready to use. So it's really, really fast to install your gen with a native extension when it's pre-compiled. But this is uncomfortable, right? Because then to publish, every time that you publish, I'm going to need to run into my machine a pre-compilation process for all platforms. So the thing that folks generally do is this. We pre-compile for the most used platforms, and we don't do this locally. We have a GitHub action. So every time that you cut a release, for example, create a tag on GitHub, this action is trigged, and it publishes the gen for you. So you don't need to do it yourself. And that's the thing that I did on FastTumble. So you can just use this. And by the way, the FastTumble, it's not really a real proposal into that sense, like, oh, I feel like everyone parsing TUML files should use this. It's just a proof of concept that shows how we can instead of writing everything from scratch, we can double check if there's a gen for this, or if we have a Rust crate that's already doing this. So we can reuse both ecosystems on Ruby. We don't need to limit ourselves. So the FastTumble goal here is not to replace any TUML parser, it's more showing that's viable. And this repository is open source here. So if you want to double check it and get some example or even contribute to this project, you can totally do it. One interesting thing about the FastTumble is it's really, really fast to parse. But when I was doing the same code to generate, just like we do on Ruby, in Ruby we have the JSON.parse method, and we have the JSON.generate method that generates the string back from a data type. And when I tried to implement the generate, it wasn't faster than the other options. So it's the best option for parsing, but it's not the best option to generate it back. So if you want to take this challenge, if you want to do some exercise and say, oh, I want to really start experimenting with Rust extensions, you can totally do this. So this is the key message. Like, I believe it's really valuable to reuse stuff that already exists instead of building them from scratch. And frequently, more than before, now you can check both ecosystems. You can check Ruby gens and check the Rust crates if you need to do a very computational intensive task. And if you have that option there, you can follow this step. It's very straightforward. And then build that gen that solves your problem. Don't need to resolve it yourself and implement from scratch. So it's pretty much this. The slides are into this link here, and thanks for listening to me.